Let's talk about system response. So if you wanted to dive a little deeper, sections 5.1 through 5.7 in the book have pretty good information in them. And as I say at the beginning of almost every one of these videos, this is just to introduce you to the topic. Likely during your career, if you find you're doing a lot of system response, you'll need to dive deeper than what this class prepares you for. Okay, so system response is going to be how does the system that you're trying to measure respond to different inputs. And so maybe you've got a spring mass damper scenario, and that's going to respond differently than just a spring mass system. And so when we're taking measurements, it's pretty important for us to understand what would we expect to see, and then is the system we're using to measure that, is it going to change the result in any way? So just to recap on the semester of where we've been, where we're going, we've talked about standards, probability, Gaussian statistics, uncertainty, fit and calibration, waveform analysis. We've talked about Wheatstone bridges, technical report writing, technical summaries, lab experiences, alternative measurements. You all now should know the size of your gulp, of course. And where we're still going is on the group project. On the lab side, we have the group project left. And on the classroom side, we have the system response, which we're talking about right now, signal conditioning, and then specific sensor types. So realistic measurement systems, we've got an ideal case where we want to measure something and we're using a sensor and a computer record the data. And really, it would be fantastic if we got exactly what we wanted to out of it. And actually, most sensors are so small that we have to put an amplifier on it. And then when we put an amplifier on there or do any other type of conditioning, there's likely going to be a change in the measure end. So we've got something out here that we're trying to measure, and this is the response. It would be awesome if we could just have it be recording exactly what was happening in reality. But as soon as we start putting an amplifier in there, some sort of computer system and filters, then it may change that result. We might also pick up some noise along the way. So that's what we're going to talk about. All right, response, fidelity to purpose, and exclude all else. We would love to have it be 100% correct. How closely does our perception or our measurements match what's actually happening? That's a good question to be asking yourself when you're taking measurements. Is this really reflecting reality, especially when you start getting more and more complex systems that you're trying to measure? How do we compare or define the relationship between what actually occurred and what was perceived or what was captured with our equipment? Good questions, right? So we look at the amplitude response, frequent response, and phase response. We're going to talk about those three and also the slew rate. Okay, so what amplitude response do we want? We've got this plot here, and if you were to pick out a sensor that was, you were to pick out an amplifier, and that's what this is doing is amplifying. So our input versus our input versus our output. So we've got our output. So if our output is 250 times our input, then we've got a gain of 250. And so it'd be fantastic if the input, as we change that voltage as we go in, we get 250 out, right? But if we follow along here, what happens at some point, our input, we don't get exactly the same amount out. And as we go further and further, that gets worse and worse. So what's happening as this input gets attenuated instead of amplified? So what is happening here? Well, we get the amplifier overload. It cannot supply more voltage than what's being put in. And so we saw this in the lab, right? We set our limitation to, and we know that there's stuff happening up here. We did a standard deviation of this line, and the standard deviation was 0. And that was a good indicator that there is stuff happening above here, but we were saturated. We could not get any more signal out of that. The amplifier was fully maxed out. And you can see when we changed the scale on it, now we could actually see what was happening above 2 volts. And so that's what's happening is maybe our amplifier gets saturated and we can't go beyond that. It will not output any more voltage. Also, frequency response, it characterizes the relationship between the amplitude and the frequency. And so maybe our input signal looks like this and our output signal looks like that. And it's because we're amplifying it. shoot, we got something different. So if we're trying to measure reality with high fidelity and we go from here to here, we're missing stuff. We're missing data. So what kind of frequency response can we get? So this is a little bit different plot now. We're looking at an amplifier, and it has a gain of around 235 or something like that. And so for every volt that comes in, we'd get 230 volts out, or maybe it's millivolts in and millivolts out. But we're multiplying it essentially by 230 or so. That's kind of what I'm picking off this plot. But look at this. As the frequency increases, we start getting less and less amplitude out. And so if we were measuring something up in this range here, we wouldn't see it as clearly. Or if we had a square wave or something like that where it had several frequencies in it, then these frequencies that are lower would be more amplified and the frequencies that are higher would be less amplified. And so they would attenuate and they would be smaller and we wouldn't be able to see them as clearly, but they'll still be there in reality. It's just our data acquisition system cannot see them or is not reproducing them for us to see and analyze. So phase response, characterize the relationship between frequency and the phase lag. And so maybe the instrument that we have or the amplifier we have automatically causes a shift in there. That's pretty important if it's dependent on time. And so phase lag is rarely zero. And really we're trying to keep it constant over time, but really we want to see, or we're going to need to know how far that phase lag is off. And these different links that I have in here, these are just to show you where I got the figures. Okay, characterize the relationship between frequency and phase lag. So we've got our frequencies here and then our phase lag. And so again, if we have our input coming in here, great. If it's 10 to the third and below, we've got no phase lag. And so it's going to represent reality very well. But as we get up here, now it's going to be off by 60 degrees. So if you think about it again, if we have multiple frequencies and some of them are down below here, those are going to reflect reality and other frequencies are going to be skewed and they're going to be offset. So that's not going to reflect reality very well. So a single stage amplifier typically will give us phase lag of 180 degrees and double stage will give us 360 degrees. And again, as long as we know what it is and as long as we know that it's consistent in the range of values that we're looking at, then we can deal with it. But it's when it is across a wide range of frequencies or we don't know what it is, then it becomes challenging. These are some of the other things that can cause phase lag: stray capacitance or inductance, wires, filters, etc. There's quite a few that we could list out here, but just the idea here is to know that as soon as you start adding things to your measurement system, you could have implications which would be negative for measuring the reality of what's happening. So what do we do? How do we know if it's okay? Well, systems driven long-term with a simple sinusoidal wave are generally insensitive to phase lag. Any time measurement, why is that? Let's go back to this first one. If we have a sinusoid and it was off when we first started recording, but then we record for 10 hours and it was only off for 0.1 seconds, then it's going to be such a small amount that it was off in the beginning that it's going to be minuscule by comparison. And so a lot of times you can fix a lot of issues with instrumentation by taking longer sample sets. Any time measurement value is worth it. Any time measurement's value or worth is independent of phase. Maybe we don't care if it's out of phase. Maybe we're not triggering anything off of it. When we do care about it is when we need real-time data. Like this happened at time equals X. That's when we need to know what our phase lag is. Or synchronized measurements. Maybe you've got a camera and a laser and you're trying to time it so the laser fires and then a camera takes a picture of it. It's going to be really important if you have that off. Anytime we're dealing with complex waves that have multiple frequencies like radio signals, yeah, we're going to need to know what the phase lag implications are. So why do we care about the amplitude, frequency, and phase response when we're picking out an amplifier or other equipment? Well, it's not always appropriate for us to spend the time analyzing the amplitude or frequency response or phase of a system. Many engineers, we simply just need to be aware of it. And if it's small enough, then we can ignore it. Okay, so now let's look at a square wave and see how our system would respond to a square wave, because that's pretty complex, right? We've got this equation that we have from before. It's example 5.1 in the book if you want to look at the square wave distortion, and also table 4-1. And so if we start including these terms for gain, so now we're amplifying it, right? We've got an amplifier in there. So we've got gain and we've got our phase shift because we know it's going to shift it because it's an amplifier, maybe 180 degrees, maybe 360, depending on what we've got. So now G sub n is the gain and phi sub n is the phase shift for the nth harmonic. So if we take each individual frequency and use figure 5.1 through 5.3 to modify the gain, so those are these figures right here. We're going to just look up values on these figures. And if we use those to figure out how they are changed, then we can actually quantify this. So if you were picking out this amplifier, the manufacturer likely has a cut sheet or a data sheet in which they have these graphs on them for that specific amplifier. And so now you can actually look at that and pick out the value and see what's happening to your signal. And so we're going to use an example that's going to be similar to that. We've got a fundamental frequency of 1,000 hertz that's happening in the real world. We're trying to measure it. And we're interested in the 15th harmonic, so n equals 15. So the frequency of interest is now going to be 2 times the nth harmonic minus 1 times the frequency. So we've got 29 kilohertz. That's what we care about, is what's happening at 29 kilohertz. Okay, so let's look at this. First plot here is, let's say that our signal is 1 millivolt. And so the amplifier is putting in 1 millivolt, and we're going to multiply that by around 250. It's somewhere in between 200 and 300. And so our amplifier is going to amplify it quite a bit. But that doesn't tell us anything about the fifth harmonic. That just tells us at that input voltage, we're going to get this specific output voltage. So in 1 millivolt, out's going to be around 250 millivolts. Okay. So if we're looking at the frequency response and the amplitude response, we're going to need these other plots. And so the frequency response of what we're interested in is at 29 kilohertz right here. And so we're going to look up 29 on this logarithmic scale. And we are going to see that we're getting a gain of 200. And so it's attenuated, right? It is not as good as it was, or it could have been, if the frequency was lower. So we've got an attenuation. We're only getting 200 out of it for our gain. Now, if we look at our frequency response, we go to 2900 on the logarithmic scale, and we pick off, 30 degrees. And so we are getting a phase shift of 30 degrees at 29 kilohertz. So what is that going to look like? Well, if we plotted this square wave at 100 hertz, at 1000 hertz, this is the output that we're going to get. So the dashed line is what we would expect, or what's happening in the real world, and the solid line is what our data acquisition system is actually reading. So you can see the response here at 1000 hertz is pronounced, at that frequency of interest, that fifth harmonic. Now, what if we changed our fundamental frequency from 1000 hertz to 2000? Now it gets worse. And so as we get higher and higher on this frequency, that fifth harmonic is going to become more and more pronounced as being not reflecting reality. So how do we measure the system response? Well, we just gave an example of a square wave, and we like to use step functions because it has all the frequencies in it. When it's going around that top corner, it has all the frequencies in it. And so it is very nice for us to give a dynamic system. We just hit it with a big hammer, or in other words, we give it a step function. We say the voltage is 0 until this specific point in time, then it goes up to 10 or whatever the number is. We get a step function like this. So this is what we feed into our system to see how it's going to respond to having this step function and how it's going to respond to all the different frequencies that are in there. So at time less than or equal to 0, we have no amplitude. And then at time greater than or equal to 0, we have amplitude. And so we're going to say this amplitude is 1 in this case. So as we're looking at this, there are a few things that we need to look at. We need to look at the rise time, or how long it takes for it to respond. So we've got a rise time. Oh, it took a while for it to get up to here. That's going to be one of our key functions or our key variables that we're going to want to look at as we select components. And then the settling time. How long does it take to get back down to be settled out at that new rate or that new value? And then the slew rate. So the slew rate is how quickly it can respond. So it's going to be this right here, the slope of this line. How fast can it respond? And so as you're going through picking out equipment, you're going to want to look at these. So the time required to go from 10% of the value to 90%. So again, we're giving it a range, and we're just, as engineers, defining what we say is the start point and the end point to measure our rise time. And then the settling time is a measure of how long it takes to get until we're close to the final value. And then the slew rate is the maximum rate of change that the system can keep up with. So you can imagine we're giving it a step function, but what if this measurement is changing rapidly? Then that slew rate it's going to make it so we miss information, miss data. So now if we understand some of this and we start looking at the response of our experimental system, we've got some different elements that feed into it. So exceeding the amplitude response of the system obviously is going to be a problem, because we cannot get a value out of that that's going to reflect reality. And then an amplifier that's overloaded is going to produce a constant voltage regardless of the input. We talked about the saturation point, where we're going to have just a single, like the standard deviation is going to be 0, so it's not going to be changing at all. And then we have problems with frequency and phase response that are subtle and therefore a lot more dangerous. They're hard for us to know that it's even happening. And so you need to be aware of it as an engineer. If you're doing measurements, you need to be aware there is a likelihood that I'm going to have a phase shift and a frequency shift. And so I'm not actually measuring the reality of these values. And so you can see we've got our input and our output. Ideally, those are the same, right? We've got a gain here, and so we're maybe amplifying it, and then we have a phase shift because maybe our system is changing the output value. You can see this looks like the input is higher than the output, and so maybe we have some attenuation, and then you can see that we do have a phase shift. It has shifted. So realistic measurement systems, it'd be awesome if we got everything to record it exactly right. That almost doesn't ever happen. The output is going to be small, so we're going to have to amplify it. We put an amplifier in. And then as soon as we do that, then we start getting the reality of all of these other things that are compounding to make our output not reflect reality. Two different fundamental types of construction. We've got mechanical and electrical systems. So I tried to get some nice pictures of electrical and mechanical systems here. But you can imagine both of them are going to behave similarly, right? They're going to both have aspects in which there's going to cause some lag or maybe some phase shift. So mechanically, that could be that it's heavy and therefore slow to respond. On the electrical side, maybe there's capacitance and inductance. And so we've got an analogy here that we can tie between those two. So as we're thinking about that, let's think about the single degree of freedom system. And so we just give it an input. What causes it to overshoot? A single degree of freedom system. Why does it overshoot? And then the question is, why does it come back to the value or equilibrium? And then what makes it settle out? Okay, keep all those in mind for just a minute. So many of the electrical systems that we have and mechanical components have similar effect on system response. And so what does that look like? Well, we have a second order mechanical systems having three basic elements: a mass, a spring, and a damper, right? And so if we go back and look at these, well, this is the answer to these, is we've got something that causes the mass to overshoot it. We've got mass that causes it to overshoot, and then it brings it back for the spring, and then it settles out because of a damper. And so similarly, or the analog between mechanical and electrical systems is we have inductance, which is similar to mass. We've got capacitance that is similar to a spring, resistance similar to a damper. So as we go through these, they are going to play similar roles. So you could look through these and see what the variables are. But let's look at a quick problem. Now, if we've got a simple system that's modeled by a spring mass system where there's a restoring force and it's proportional to the distance, so F equals kx, then we've got a linear spring or a torsional spring. I think this was supposed to show up after this one. Okay, so if we have our omega is equal to square root of the spring constant times our gravitational constant divided by the mass, we can actually now figure out how this system is going to respond to an input, right? Same thing with the damper. If we have a damper on there, now we've got this dash pot that's going to slow that thing down. Now we've got critical damping and we've got the damping ratio to deal with. And so our force is equal to our negative damping coefficient with the displacement terms. So if we look at critical damping, like we usually do in engineering, that is the best case scenario. Critical damping is if it damped out exactly at the right rate that we need. And so we could calculate that out and figure out what it is. And then we can say, well, how does that critical relate to the actual? Psi, that is our damping ratio. And so you could calculate out what that damping ratio is. So if we look at the psi variable as on a displacement versus time plot, you can see that this overshoot, we go way over the mark and then it takes a minute for our system to respond. And so that's underdamped. We don't have very good damping on that. But what happens if we go to the other end of the spectrum and we say that it's overdamped? Well, it's going to take forever for us to get to that final value. And so really this critically damped, where psi is 1, it'd be ideal. That means we're going to get to the result as fast as possible without overshooting it. And so we can calculate these out for our system. So if we think about this for a minute and we think about a mechanical beam used as a scale, and so you could put different things on these and see how it reads the value, or comparing the weights. And let's say it's 100 grams, and the pointer can tell the difference up to plus or minus 5 grams. And so we take the 100 gram standard and we put it on the left pan, and then we put a 99 gram on the other side. What's going to happen? So if we put that 99 gram on the other side, then it's going to lift off the 100 gram, maybe a little bit, and it will point to the difference between the two. And then it might oscillate around the correct weight, and eventually it's going to settle out showing 1 gram. But how long will that take? Well, it depends on the damping present. And how could we make that, how could we increase the damping of it? Well, you could maybe fill it up with molasses. There's probably several things that you could do to increase the damping so then it would settle out at a faster rate. So an underdamped system is going to oscillate around the final value, and it's going to keep going until it eventually settles out. And so what's going to settle it out if there's nothing in there? Well, it could be the air current. It could be a little bit of friction in the pendulum or the knife edge. It could take an inconveniently long amount of time. If we did put a damper on there using molasses or something like that, then it's going to damp out faster. It won't oscillate, and it will get to the value, but it won't take as much time. Okay, so now just zooming back out, a critically damped system settles out to the correct value without any overshoot. It still takes some time to get there, but you get there faster. Now, if you can tolerate, so this is the critically damped, right? It's the ratio of 1. So it's still going to take a while, but if you can tolerate a little bit of overshoot and then bring it back, look at this. We've got this equal to 0.7. So this is the ideal damping that we're shooting for, 60 to 70% critical damping. And so this 0.7 or 0.707, if we've seen it again, this is the shortest settling time. And so that is the ideal. This is what you're usually shooting for unless you can't tolerate any overshoot. So most instruments are shooting for this 0.707 or 60 to 75% of the critical damping. Okay, so why do we care about all this? Well, again, we're designing and building things that are mechanical and electrical, and the response that they have to the inputs is going to be important. And so thinking through what's going to affect this, is it going to phase shift? Is it going to amplify it? Is it going to have a frequency shift? What's going to happen to the outcome? That is the most important thing to keep in mind, is the reality is probably not going to match what we're measuring. And so we need to be very cautious.